Quantum physics is the study of the very small particles that are smaller than atoms. Think electrons, protons, and neutrons. And here's the kicker. These particles don't behave like anything you've ever seen before. Particles can act like waves, and waves can act like particles. Picture a cat that's both alive and dead until you peek inside the box. That's Schrödinger's cat, a famous thought experiment in quantum physics. When particles become entangled, their states are linked, no matter how far apart they are. Change the state of one, and the other changes instantly, even if it's on the other side of the universe. Einstein called this spooky action at a distance. Quantum physics isn't just theoretical. Here are the 5 things about quantum physics you might know them wrong. First, we have the quantum entanglement. It is a complex phenomenon in physics that is usually poorly described as an invisible link between distant quantum objects that allows one to instantly affect the other. Albert Einstein famously dismissed this idea of entanglement as spooky action at a distance. In reality, entanglement is better understood as information, but that's admittedly bland. So nowadays, every news article, explainer, opinion piece, and artistic interpretation of quantum entanglement equates the phenomenon with Einstein's spookiness. The situation has only worsened with the 2022 Nobel Prize in Physics going to Alain Aspect, John F. Clauser, and Anton Zeilinger for their quantum entanglement experiments. But it's time to cut this adjective loose. Calling entanglement spooky completely misrepresents how it actually works and hinders our ability to make sense of it. In 1935, physicist Erwin Schrödinger coined the term entanglement, emphasizing that it was not one but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. He was writing in response to a famous paper by Einstein, Boris Podolsky, and Nathan Rosen that claimed quantum physics was incomplete. The New York Times headline read, "Einstein attacks quantum theory," which solidified the widespread perception that Einstein hated quantum physics. The EPR argument concerns the everyday notion of reality as a collection of things in the world with physical properties waiting to be revealed through measurement. Einstein's theory of relativity fits into this understanding and says reality must be local, meaning nothing can influence anything else faster than the speed of light. But EPR showed that quantum physics isn't compatible with these ideas, that it can't account for a theory of local reality. In other words, quantum physics was missing something. To complete quantum physics, Einstein suggested scientists should look for a deeper theory of local reality. Many physicists responded in defense of quantum theory, but the matter remained unresolved until 1964, when physicist John Bell proposed an experiment that could rule out the existence of a local reality. Clauser was the first to perform the test, which was later improved and perfected by Aspect and Zeilinger. A typical article about entanglement tells us it arises when particles interact to create a link, which persists no matter how far apart those particles are. Moreover, actions taken on one particle instantly affect the other, or so we are told. But, and here's the thing, even many experts get wrong. Quantum physics doesn't say that. Quantum physics says nothing about how the world is. Instead, quantum physics only describes the experiments we do to test our theories of how the world works. It gives us probabilities for the outcomes that may happen in an experiment. The compulsion to interpret quantum physics concepts as prescriptions for physical reality derives from the unfortunate way we traditionally teach physics. Today, you can follow in their footsteps by creating entanglement and processing the correlated quantum information on a real quantum computer. Einstein wanted all of nature identified with a simple and compact classical description. But we now know that quantum information provides the most accurate description of nature, which is written in a language we do not speak. We thought computers were the ultimate tool for this purpose, but we were wrong. Scientists now believe the ultimate machine is a quantum computer, the full potential of which we have yet to realize. Determining when quantum computers will become ubiquitous and what problems they will solve is an exercise in crystal gazing. However, we already know they can solve a small list of problems such as factoring numbers, searching databases, or simulating chemical reactions. If you have such a problem, you might be in the market for a quantum computer. You'll love it. Einstein, on the other hand, would have hated it. Next, imagine touching the surface of a pond at 2 different points at the same time. Waves would spread outward from each point, eventually overlapping to form a more complex pattern. This is a superposition of waves. Similarly, in quantum science, Objects such as electrons and photons have wave-like properties that can combine and become what is called superposed. While waves on the surface of a pond are formed by the movement of water, quantum waves are mathematical. They are expressed as equations that describe the probabilities of an object existing in a given state or having a particular property. The equations might provide information on the probability of an electron moving at a specific speed or residing in a certain location. When an electron is in superposition, its different states can be thought of as separate outcomes, each with a particular probability of being observed. An electron might be said to be in a superposition of two different velocities or in two places at once. Schrödinger proposed that the cat could be said to be both alive and dead, in a superposition of states until the box is opened, and that the act of observation randomly determines whether the cat is alive or dead. Schrödinger intended the example to demonstrate what he saw as the absurdity of quantum science. In mathematical terms, superposition can be thought of as an equation that has more than one solution. When we solve x squared equals 4, x can either be 2 or -2. Both answers are correct. Next, we have the wave-particle duality, a concept that reveals the enigmatic nature of both light and matter. This duality suggests that entities such as light and electrons possess both wave-like and particle-like characteristics. In 1905, Einstein demonstrated, through experimental evidence, that light, which had long been considered a form of electromagnetic waves, must also be thought of as particle-like, localized in packets of discrete energy known as photons. The mystery deepened with the observations of the Compton effect in 1922 by American physicist Arthur Holly Compton. His findings could only be explained if light exhibited both wave and particle properties. In 1924, French physicist Louis de Broglie proposed a radical idea: not only light, but also electrons and other discrete bits of matter, which had been conceived solely as material particles, possess wave properties such as wavelength and frequency. By 1927, the wave nature of electrons was experimentally established by American physicists Clinton Davison and Lester Germer, and independently by English physicist George Paget Thomson. These experiments provided concrete evidence that electrons, like light, exhibit wave-particle duality. The culmination of these discoveries came in 1928 when Danish physicist Niels Bohr introduced the complementarity principle. Bohr's principle offered an understanding of the complementary relationship between the wave aspects and the particle aspects of the same phenomenon. It emphasized that these dual characteristics are not mutually exclusive but rather two sides of the same coin, each offering a different perspective on the nature of reality. Now we come to quantum tunneling. It is a quantum mechanical phenomenon where a particle can penetrate through a potential energy barrier that is higher in energy than the particle's kinetic energy. This seemingly magical property of microscopic particles plays a crucial role in explaining several physical phenomena, including radioactive decay. In classical physics, a particle hitting a barrier higher than its energy would simply bounce back. But in the quantum realm, particles do not always behave as we would expect. Due to their wave-particle duality, there's a non-zero probability that a particle can tunnel through the barrier and appear on the other side. One interpretation involves the Heisenberg uncertainty principle, which defines a limit on how precisely we can know both the position and momentum of a particle simultaneously. This principle suggests that there are no absolute certainties, only probabilities. Therefore, the probability of a particle existing on the opposite side of a barrier is never exactly zero. Quantum tunneling isn't just a theoretical curiosity, it has practical applications that have revolutionized various fields. At the end, we talk about Heisenberg's uncertainty principle. Named after the German physicist Werner Heisenberg, who introduced it in 1927, this principle fundamentally challenges our understanding of measurement and certainty. Heisenberg's uncertainty principle states that for particles exhibiting both wave and particle nature, it is impossible to accurately determine both their position and velocity simultaneously. Heisenberg discovered this principle while trying to build an intuitive model of quantum physics. He realized that certain fundamental factors limit our ability to know certain quantities. Essentially, this principle highlights that any attempt to measure the position and velocity or momentum of microscopic matter waves will introduce an error. The product of the error in measuring position and momentum is always equal to or greater than an integral multiple of a constant, known as Planck's constant. As we conclude our journey through the enigmatic world of quantum physics, we find ourselves standing at the threshold of uncharted territories. From the mysterious behavior of particles to the concept of superposition to Heisenberg's uncertainty principle. What did you understand? Let us know in the comments.